I want to start by giving thanks to the organisers for allowing us to discuss our research and present our paper and its findings. Our work began as a reflection of the contemporary culture of geometry-driven design in architecture, in which we identified that there stands an institutionalised segregation forming a rift between the cooperative fields of architecture, structural engineering and construction. Therefore, in rebuttal to this separation, it was our approach to develop a workshop to investigate the contribution of material and fabrication-aware design methods to aid in the creation of space for uncertainty and the potential for embodied learning. Within the workshop, participants were to investigate and develop a design for assembly techniques and configurations for the production of a masonry block using both analog and digital manufacturing techniques. The first day began with a practical exercise which would look to instill an understanding of the fundamentals of construction logic and material functionality through fulfilling a simple concrete casting procedure using a provided kit of parts. At this stage, the focus was for the participants to gain an understanding of the material limitations and the need for adjustment to unforeseen issues in real time. A critical step was to engage the participants in a post-exercise review, as this would start developing a cognitive bridge between reflection and action. In creating space for uncertainty and learning, it would require us to detach the process from the typical format of architectural curriculum that commonly prioritizes design outcomes over experimentation. Developing a project that would remain engaged with digital design but treat it as a secondary application to that of the physical production. In turn, integrating materiality and manufacturing into the early stages of design development establishes a fabrication-aware cycle that closes the loop between design and production. To accommodate the cycle of iteration, we orientated production around three methods: manual hot wire cutting, robotic tooling, and 3D printing. Progressing onto the design stage of the workshop, we began by leading a short course for the use of digital design and the essential machine software, followed by 3 days of the participants developing their individual designs. On the fourth day, the group was asked to cross-examine each other's designs and agree amongst themselves on a singular design to take forward into production. Then apply this design to a scaled structure to validate its use within a compression-only method of representation. Having finalized their design, they would need to develop a negative formwork through physical techniques and digital templates that consider the limitations for production, such as working precision, production time, material efficiency, and cost and scalability. Furthermore, within the images here, you will see a prototype for a 3D printed formwork which became an example of the unknown consequences encountered throughout fabrication. While preparing the prototype to print, they discovered that due to factors such as material type and thickness, the print was expected to take in excess of 46 hours. Furthermore, once printed, due to the orientation, the print direction had caused topographical markings along one of the surfaces exposed to the concrete, highlighting the critical reason why prototyping is key to the cyclical process. Alternative methods of fabrication presented a higher degree of complexity, such as the use of both the manual hot wire cutting and the robotic tool system. In the upper strand of images, you will see a process in which the students were required to create a number of template designs to be able to successfully guide the form by hand. While in the lower strand of images, you can see the process of the robotic tooling system, which involved a less interactive approach but required the development of predefined programming. At this stage, the group would need to review their progress and decide on the most efficient method to carry forward, for which they determined would be the 3D printed mold. Now that the participants had completed all practical aspects of the workshop, they would now review the process of fabrication and would be able to expand this criteria with any additional measures of efficiency that they had discovered along the way. The findings were weighed in 2 stages to be able to determine their efficiency. First, establishing how each criterion would be assessed. For example, working precision would be measured in millimeters, production time in minutes and hours. Then each criterion was graded against a scale of efficiency as shown in the upper table. In the lower chart, you will see indicated that the 3D printing scored the highest for efficiency across most fields. This was followed by both the manual hot wire cutting and the robotic tool system, both scoring the same degree of efficiency but across different criteria. Although the 3D printing scored the highest for efficiency, at scale the efficiency decreased exponentially due to the number of molds that would be required. Therefore, it was found that the most scalable method was the robotic tool system. Despite limited interaction for this workshop, for production, once set up, it proved to be a quick and low-cost method for fabrication. To conclude, by introducing a short-term project at the beginning of the academic year, participants can be introduced to fundamental fabrication processes that build a framework of inherited knowledge that can be later deployed within their studies. By orientating the workshop around a design outcome, it accommodates the contemporary academic structure while embedding learning through a fabrication-aware design approach. Furthermore, it awards participants the opportunity to engage with reflection in action and reflection on action within their learned experiences. Therefore, our findings indicate that the use of physical models did not only contribute to the active embodied learning and self-reflection through redefining the design development process, but also created a space for indeterminacy and surprise within education.